Have you ever stared at a polynomial graph with all its twists and turns and just wondered, how does it know what to do? It's like there's a secret code buried deep inside the equation, telling it exactly where to cross the x-axis and where to turn around. Well, today we are cracking that code, and it all starts with the two basic moves a graph can make. So whenever a polynomial graph gets to the x-axis, at its roots or its zeros, it really only has two choices. It can slice right through it, which we call a cross, or it can just kind of tap the axis for a second and then boomerang right back in the direction it came from. We call that a bounce. So that's the big question, right? How can we possibly look at some messy equation, a bunch of x's and exponents, and know beforehand if the graph is going to cross or if it's going to bounce? What's the secret signal inside the math? Well, the answer, believe it or not, comes down to one single, really powerful idea. This is the key to the whole thing. The secret is a concept called multiplicity. Okay, I know, that definition looks a little formal, but the idea behind multiplicity is actually super simple. It's really just a way of counting how many times a specific root, or zero, pops up. When you've got a polynomial all factored out, you just look at the exponent on each piece. See that little k up there? That's it. That number is the multiplicity. All right, so now we know what multiplicity is. It's just a number, an exponent. So let's get to the fun part. Let's decode the rule that tells us how this one little number controls everything. And here it is. The rule is just shockingly simple. If the multiplicity is an even number, like 2, 4, 6, the graph bounces off the x-axis. Think of it like hitting a trampoline. But if the multiplicity is an odd number, 1, 3, 5, the graph crosses right through the x-axis, like walking through a doorway. And check out that special case for a multiplicity of 3. It's still odd, so yeah, it crosses, but it kind of flattens out for a second, creating this cool little S shape as it goes through. Now, theory is one thing, but seeing this rule in action is where it all starts to click. So let's get our hands dirty and work through some actual examples. Okay, let's break this one down. First up, we have a 0 at x equals -1. The factor is x plus 1 squared. The exponent, the multiplicity, is 2. Is 2 even or odd? It's even. So you know what that means? The graph bounces. Next, at x equals 3, the factor is just x minus 3. You don't see an exponent, which means it's kind of like there's an invisible 1 up there. 1 is odd, so the graph crosses. And finally, at x equals 5, the multiplicity is 3. Odd again, so it crosses, but it does it with that little S-curve wiggle. See? It's that easy. All right, now for a problem that isn't so nicely packaged for us. When you see a polynomial like this, your first move, always, should be to look for a greatest common factor, the GCF. In this one, you can see that every single term has at least an x squared in it. So we're going to pull that x squared out front. That is the critical first step. So what are we left with inside the parentheses? We've got x squared minus 2x plus 1. And if you've been practicing your factoring, you might recognize that pattern. It's a perfect square trinomial. That factors down really nicely into x minus 1 squared. And just like that, our polynomial is now completely factored. And now we get to use our rule. That x squared out front, that gives us a 0 right at x equals 0. The multiplicity is 2, which is even, so it bounces. Then we have the x minus 1 squared factor. That gives us a 0 at x equals 1. Its multiplicity is also 2. Even again, so it also bounces. Can you picture it? This graph is going to come down, kiss the axis at 0, go up for a bit, then come back down and kiss the axis again at 1. A double bounce. Okay, let's flip this whole thing on its head. What if we work backward? Can we build a polynomial if we just know how we want it to behave? Let's try. We want a graph that bounces at x equals -2 and crosses at x equals 4. Well, we know our rules. A bounce needs an even multiplicity. Let's just use 2 to keep it simple. A cross needs an odd multiplicity, so we'll use 1. Now, we just assemble the pieces like building blocks. A 0 at -2 gives us the factor x plus 2. A 0 at 4 gives us the factor x minus 4. All we have to do is take the multiplicities we picked, 2 and 1, and slap them on as exponents. And there you have it. We've literally designed a polynomial from scratch to do exactly what we wanted it to. So this whole multiplicity thing is an incredibly useful tool, but like any powerful tool, there are a couple of really common mistakes people make. Let's go over the two biggest traps so you can sidestep them completely. First, and this is the big one, don't mix up the main rule. It sounds simple, but in the middle of a test, it's so easy to get it backward. So just burn this into your brain right now. Even means bounce. Odd means cross. Say it with me. Even, bounce. Odd, cross. Get that down and you're halfway there. The second trap is a little sneakier. Remember in that second example when we factored out an x squared? A lot of people do that, and then they completely forget that the x squared itself represents a 0. That x squared means there's a 0 at x equals 0, with a multiplicity of 2. It's so easy to factor it out and then just ignore it, but that 0 at the origin is a crucial part of the graph.
So at this point, you might be thinking, okay, this is a neat math trick for sketching graphs, but does it actually matter in the real world? And the answer is a huge yes. Let me show you a really surprising place where this shows up.
Believe it or not, this all ties into mechanical engineering. When engineers are designing something like a car suspension system, they model the vibrations with polynomial equations. And a repeated root, which is just a 0 with a multiplicity of 2 or more, represents something they call critical damping. That is the absolute sweet spot where the suspension absorbs a bump perfectly without bouncing up and down forever. So that bounce we see on the graph, it's directly connected to controlling the bounce you feel in your car. So what have we learned? Multiplicity isn't just some random rule. It's the secret set of instructions telling a graph exactly how to behave when it hits the x-axis. You now have the power to look at an equation and predict whether it's going to bounce or cross. But that leaves us with one last big question. We know what the graph does at its roots, but what on earth is telling it what to do in all that space between the roots?